Welcome back, everyone, to day 2 of water quality in the distribution system. I'm so glad that you are back with us. As we wait for everybody to get logged in, we'll start again at the top of the hour. If you happen to have any questions from yesterday, feel free to put those into the chat and I will keep them on the list for later today. Otherwise, we'll get started here in just a couple minutes. Welcome back, everybody. My name is Lori Krings. I am the moderator again today, and we are in day 2 of water quality in the distribution system. And I'm so glad that you guys are all back. We're going to take a look briefly at our plan for today. You'll find that it's very similar to the plan from yesterday. And I will once again share these slides with you momentarily. Really, the flow of today will be very similar to yesterday. Not much has changed as far as housekeeping or the presentation or the break or anything like that. The biggest thing of note for today is that if you do want that certificate of attendance, if that matters to you, today is the day that we do need you to grab that SurveyMonkey link out of the chat, which will be placed there at near the end of the session today. And just keep in mind that it's only active for 24 hours, so it does expire. So again, if that certificate of attendance matters to you, please make sure to grab that SurveyMonkey link at the end of the session today. And just a short reminder that if you do have questions, please do pop those into the Q&A or into the chat, and I will reserve them for our time later. Okay, well, we'll go ahead and get started then, and I'm going to throw it right over to Daryl to get us going.
All right, thank you, Lori, and thank you, Ingrid, for working behind the scenes to make this all happen. Okay, so welcome back, everyone, to day 2. Greg, through a scheduling thing, is actually providing a different training through Syracuse University as we speak. So he's training right now. I will be taking on the entire session today. Today, we're going to cover 3 main topics: disinfection and disinfection byproducts, what are the elements of a sanitary survey, and we'll cover some distribution system sampling and monitoring. So chlorine disinfection and disinfection byproducts. So why do we add chlorine? So you can see from this chart that since we started adding chlorine, there's been a significant decrease in the rate of death from typhoid fever, for example. There used to be thousands of deaths due to waterborne illnesses, but nobody really understood why. In the 1670s, we were first able to observe these microbes using a microscope. In 1854, John Snow figured out that cholera was caused by waterborne, came through the water. That's really interesting. If you can get time and you want to research John Snow and the Broad Street Pump cholera outbreak in London, it was really an interesting thing, and how he found, he determined that the source of this cholera was through drinking water. In the 1860s, Louis Pasteur developed the germ theory. His theory was that microorganisms such as bacteria and viruses are the primary causes of diseases. And then in 1908, New Jersey had the first system in the US to chlorinate drinking water. So you can see where this line signifies 1908. We had some high typhoid fever outbreaks prior, and then through time in the institution of chlorination and drinking water systems, we've seen that reduce. And to the point where in 1945, we were in the US water industry, and we're down to less than a death per 100,000 people. So as you can see, numbers were well over 20, well into the 20s at some point. So that's a significant decrease. So chlorine disinfection is an important tool that we use. So we're trying to use chlorine to either remove or inactivate different pathogens. Pathogens in drinking water are disease-causing microorganisms such as bacteria, viruses, and parasites. They can contaminate our water supplies, and they can make people sick. So we're using coliform as an indicator organism. So the idea is that when we test for total coliform, it's just giving us an idea whether the water it's possible that the water contains some of the more concerning things, such as E. coli or fecal coliform. So just because a test comes back for total coliform doesn't mean that we have that it's dangerous. It's just an indicator that maybe we need to do some additional investigation. So, and now E. coli, there's an MCL under the revised total coliform rule. So if you were to have a test for total coliform done, and it came back positive, you would have to follow up with an E. coli test to confirm that you didn't exceed the MCL. So another method an indicator that we can use is we can monitor for heterotrophic bacteria. So heterotrophic plate count is an indication. It's an indication of background levels of microbial activity. But once again, it doesn't indicate for certain that we have a problem. It just indicates that there could be a problem. So HPC counts can range. Quite often you'll find water that is total coliform negative, but we have some heterotrophic plate count numbers, and plate counts in potable water above 500 CFUs. A CFU is a colony forming unit. So they count the number of dots, little units that form on this film, and give you a number. Now, if we see an increase, that can also indicate that we've got a problem in the system. We could have our chlorine residual may have dropped. There could be biofilm. There could be something introduced into the system. So it's an important indicator. I'd say the majority of systems probably don't test for HPCs. Quite often larger systems and those that have large laboratories, quite often surface water plants, will, in addition to doing total coliform testing, will do HPC testing. So what can we do to protect our distribution system? So the two most important ways that we can do that is to maintain continuous positive pressure. So if we have positive water pressure, then if we've got a hole, as shown in this pipe, we've got positive pressure, the water should be leaving the pipe, and we shouldn't be getting the water to come in this water that has potentially contaminated with E. coli shouldn't get in if we've got positive pressure. And the other thing is just to maintain the physical integrity of the distribution system. That means that we don't have holes or leaks in our pipes. So even a small crack can provide a pathway for soil containing large numbers of bacteria to enter the system during a low pressure event. Cross connections are another way that we can have things enter. If you had some sort of organic that came in, it could potentially be food for any of the bugs that we have. And then a free chlorine residual is the final backup barrier to protect our drinking water if something were to enter through this. So we want to make sure that we've got continuous positive pressure, that our system is tight, that it doesn't have any leaks, and that we have a free chlorine residual. And the chlorine residual is great, but if we're in a situation where we've got something that gets into our distribution system and we use up all our chlorine, then there isn't any more available to act on any more of the bugs. All right. So there's three main types of chlorine disinfectant. So we've got gas chlorine. Gas chlorine comes in cylinders. It's 100% available strength. And, it's a very, very potent a disinfectant form of chlorine. We've got sodium hypochlorite or liquid chlorine, comes in these type of plastic totes. They come in 55-gallon drums. It comes in smaller drums as well. And that's usually 5.5 to 12.5% strength. My experience is it tends to be more on the 12.5, the higher end of that. And then we have calcium hypochlorite or solid. That comes in these pucks. It's also called HTH. And the strength of this is 65 to 75%. So it's got a higher strength. It's tends to be easier to deal with, but you've got to dissolve that. So free chlorine, when we talk about free chlorine, it's made up of two different things. There's a hypochlorous acid and a hypochlorite ion. We'll get into that a little more further about what the benefits of each of those are. We talk about gas chlorine. The issue with gas chlorine is the potential for major human health issues. If you've got a leak of a gas chlorine leak will kill just about everything in its path. So I would assume that there is nothing living anywhere close to that gas chlorine cloud in that photo. And then chloramines it's a fourth. It's a little different than, it's not actually just chlorine. With chloramines, we're going to take 5 parts of chlorine. We're going to add ammonia to it. And so we're going to measure that as a combined or a total residual. So it's a little different. It's taking chlorine, it's adding ammonia, and then that's our disinfectant. Chloramination, ammonia is added to water that has been treated with chlorine. The added ammonia then reacts with a hypochlorous acid in the water, forming this long-lasting disinfectant. So one of the benefits of chloramines is that it does last. It doesn't dissipate as quickly as free chlorine. So I had mentioned the hypochlorous acid and the hypochlorite ion. So pH has an effect on what form we're going to have, whether we're going to have hypochlorous acid or if we're going to have the hypochlorite ion. And so as you can see here, at the low pHs, we tend to have the hypochlorous acid, and at the higher pHs, we have the hypochlorite ion. Now, the acid is more effective, and it has a better ability to oxidize pathogens. So we would tend to think that we would want to be on the lower pH from that standpoint to have the the better ability to combat the pathogens. So at a pH of 7, which is neutral, we've got a 80% is hypochlorous and 20% as hypochlorite ion. So that's typically a good spot to be in. So this is one of my favorite charts, graphs, because it helps to explain a difficult topic with the application of chlorine. So when we look at this chart, this area in blue is as we on the left we have chlorine residual. So that's showing what we have for chlorine residual as we add chlorine across the bottom. So as we add chlorine, you'll see this blue area. The chlorine is destroyed by reducing compounds. So we're adding chlorine, but we're not seeing any residual increase. Okay. And so as we continue to add chlorine, we get into the next phase, the green phase, and that's where chloramines are produced. And so chloramines are the things that cause the odor and taste complaints. And so I've seen it quite often. I've talked to a lot of operators who, they get reluctant. They get into this phase and they're reluctant to add chlorine because they just seem to get more complaints. They get more calls from residents and consumers about complaining about the smell of their water, the taste of the water, and things like that. Well, you'll note that we get to a certain point and it starts to drop off. So what happens is we get into the next phase and we're starting to destroy those chloramines. Our chlorine residuals actually start to drop, but we're destroying the chloramines as we continue to add chlorine. And then we get to the magic point, the break point. So at this point, pretty much all the chlorine that we add results in a chlorine residual. So that increases our free available residual continues pretty much as we add it, the chlorine residual goes up. So now we've hit that sweet spot. We don't have the taste, we shouldn't have the taste and odor complaints, and we're getting that free chlorine residual, which is what we were looking for. So what are we learning from this graph? We see the effects of the reducing compounds, the effect of organic compounds, and such as ammonia to form these chloramines. And then we start to see the relationship between the dose and the demand, and also the total residual is combined plus free. So that's shown a little better on this slide. Residual as chlorine is added. You see we've got this combined chlorine. This is the stuff that's basically used up by the chloramines. And then we've got a free residual. And all that together combined is the total residual. So we can look at this in a little more detail, throw in some numbers to help make it make sense. So if our dose, what we want to apply is going to be equal to our demand, and that demand is a combination of the chlorine being used up by reducing compounds. That was where it was going nowhere as we added it, and then the combined chlorine, which is the chloramines being affected, and that'll leave us with a free residual chlorine. So in this case, we dose at 1.5 parts per million. We've got a free residual remaining of 1 part per million that we know then that our demand was a 0.5 part per million. So we're on to our first poll. What dosage should be applied to drinking water with a total demand of 0.4 milligrams per liter or parts per million if the intended free residual is 1.2 milligrams per liter? All right. We're starting to get responses. All right, looks like we've got, geez, a good portion of our responses are in. Okay, we have, as you can see, we have 72% of the people saying D. We've got 22% saying A and 3% saying each of B and C. So let's move on and we will look at the next slide and see how we come up with the answer. All right, so what dosage should be applied? If we add the demand and the intended residual, we'll find the dose. So our demand was 0.4 milligrams per liter, and we want to have 1.2 milligrams per liter. So it's simply adding 0.4 to 1.2, and that gives us 1.6 parts per million. Good job, people. All right, so I think we talked quite a bit yesterday about the pounds formula. And once again, the pounds per day and the pounds formula is the million gallons per day, our flow, multiplied by our parts per million or milligrams per liter, and then multiplied by the weight of water per gallon. So in the case of a gas chlorine system, we've got this gas feeder, and it's called a rotometer, and it will provide us, we can enter in on that. We can put in what we want as far as the number of pounds that we will that it will apply in a day. So that's how we work it for gas chlorine. And we can do a gas chlorine feed rate calculation. So in this calculation, what is the feed rate setting for gas chlorine in pounds per day if the plant flow of 1.2 million gallons a day and the required dosage concentration is 1.5 milligrams per liter? So in our pounds formula, we're going to plug 1.2 million gallons per day in for flow, and we're going to have 1.5 parts per million for the dosage, and our 8.43 does not change. So if we're looking for the chlorine feed in pounds per day, we've got 1.2 million gallons per day times 1.5 parts per million times 8.34 pounds per gallon. We multiply those out, and we get 15 pounds per day. All right. So next we're going to look at calculating feed rates for sodium hypochlorite or liquid chlorine. So this is a little different because with gas chlorine, we had 100% strength. So we didn't have to deal with that percent strength. So we still have the same, the top of the equation is still the same. And that's going to calculate the pure chlorine. The bottom, we're looking at that percent strength. We need to account for the fact that it's not 100%. And then we're going to divide by the weight per gallon, and that'll give you the number of gallons you needed per day. All right. So the weight per gallon in our equation is for chlorine, and any other, if you're adding phosphate, you're adding other chemicals, you can use the same formula, but you need to take into consideration the percent strength and the specific gravity of the chemical that you're adding. So the specific gravity it's the comparison of the weight of that material or that compound, that chemical, in comparison to the weight of water. So if you have a specific gravity that is less than 1, then that means it's lighter than water. And if it's greater than 1, then it's heavier than water. So water specific gravity is 1. All right, so that's going to make our equation a little bit different. So in this example, we have a feed rate for 12.5% liquid chlorine. We're saying that liquid chlorine has a specific gravity of 1.2. We have a plant flow of 500,000 gallons a day, and we want a dosage to be 0.9 parts per million. So we're going to use the pounds formula. We're going to plug it in. We're also going to take into consideration that we have to put in our percent strength and our specific gravity in this case. So our flow is 500,000 gallons a day. Our concentration is 0.9 parts per million. We've got the weight of water. Our percent strength, so 12.5, works out to 0.125. And then we've taken the specific gravity of 1.2, multiplying by the weight of water. And that gives us 3 gallons per day. So one thing to note here is that I think if you take this 1.2 and you multiply that by 8.34 to determine the actual weight per gallon, pounds per gallon of chlorine, you'll find out that it's roughly 10. So quite often myself, I just remember that chlorine, liquid chlorine at 12.5% solution is generally 10 pounds per gallon. So I skip this step when I do it, but you're welcome to keep it in there for yourself if you like. So if we're feeding liquid chlorine, this is what our pump might look like. So this is an LMI, positive displacement pump. And can note on there that the placard shows that this pump is capable of pumping a maximum of 0.58 gallons per hour, which is important because, that helps us determine where we want to set our pump. And that maximum is when the speed and how fast the pump pumps, and the stroke, how long each stroke is. That assumes that at max flow that they're both at 100%. So we want to look at a chemical feed pump output. If the chemical feed pump is rated for a maximum flow of 0.58 gallons per hour, what is the actual output of the pump if both the stroke and the speed are set at 70%? So typically we don't want to have a pump that we run full out max, because if for some reason we have the need to increase, we have to add more chlorine than we normally are, we're limited and we can't do that. And we don't want to have a pump that we have to operate at the bottom or the minimum of its range as well. All right, so the actual output, if we've got that of that, is going to be our max output multiplied by the percent stroke and the percent speed. So in this case, we're saying that stroke and speed are going to be 70%, or for our formula, we're going to use 0.7. So if we do that, 0.58 GPH multiplied by 0.7 speed by 0.7 stroke gives us 0.284 gallons per hour. So that, if you note, that's about half of what the pump is capable of producing. So that's usually a good spot. That's a good spot. If you can be there, that allows you plenty of adjustment on the high end or the low end to make that pump work for you. So if you were to design a pump and you need to have a pump that can produce, reliably produce 0.284 gallons per hour, this would probably be a good pump for you. Now, if we want to know how much that's going to put out in a day, we just multiply the gallons per hour by 24 hours a day, and that'll give us gallons per day. And that can be important because, if you want to set it up so you've got a day tank, so you know that this tank is going to produce, it's going to have enough chemical just for the day. So I can, if something goes awry, I know I'm not pumping too much chlorine, then, you would know that you would need a day tank that's, somewhere over 7 gallons to make sure that you have enough to pump what you need. All right, so now we're on to the second poll. And this poll is determine the resulting free chlorine residual if a flow of 0.8 million gallons a day has a gas chlorine feed rate of 13.4 pounds per day, and the total chlorine demand is 0.5 part per million. As if it appears as if we have most of our answers in, then we'll go to the solution. All right, I hope that everybody has had an opportunity to work on this. Looks like we've got just about 80% of the responses. Okay, so let's all right, so Lori shared the results here. So we have 59% saying B, 1.5 parts per million. We've got 18% at 2 parts per million. We've got 15% at 1, and we've got 9% at a half a part per million. So let's see how we come up with our answer. Okay, so the first thing we do is we're going to solve for the dose. So to solve for the dose, we're going to take the pounds per day that we were given, 13.4. We're going to divide that by the flow of 0.8 mgd and multiply that by the weight of water. So it's 13.4 divided by 0.8 divided by 8.34, and that gives us 2 parts per million, or 2 million milligrams per liter, which was A. That's the start, but then we have our next step is determine the residual. So if we take our half a part per million that that was in total chlorine demand, and we subtract that from our 2, we get 1.5. So you'll notice that it's a little tricky with some of these responses, because we gave you the 2, and if you stop there, then you might say give one answer, and we have the half a part in here, so it's a little bit tricky on those responses. Okay, so we mentioned the different pathogens, and that there's bacteria, virus, protozoans, and one of the important things about this is that when it comes to bacteria, we actually destroy those. So the bacteria are killed through the process of disinfection, whereas the viruses and protozoa are just inactivated. So they may remain alive, they're just not allowed to replicate or reproduce, so they can't continue to cause problems. So we'll talk about inactivation when it comes to viruses and protozoans. So chlorine its effectiveness is based off of 2 major things. We've talked quite a bit about the residual concentration. We want to have good chlorine residuals out in our distribution system in case there's anything out there that we need it for, right? But the other key component is contact time. So we have a combination of both the residual concentration and the time for it to act on the bugs. So for viruses, they require 4-log treatment, and it's a combination of both the removal, which could happen at a treatment plant, where we're going through the different processes for treatment to remove the viruses, and then the other side of it is we can get some from the inactivation through things such as chlorine. So it's a 2-part thing that add up to that 4-log removal, and that inactivation means that 99.9% of the viruses were confidently removed through the process. So we want to achieve at least that. And as you can see from this chart, it's dependent on both temperature and pH. Those are the factors that determine how much time, these numbers here are time, that chlorine needs to be in contact in order to meet our requirements. So if we look at a temperature of 10 degrees Celsius, and we look at a pH of 7.5, so the 7.5 falls into the 6 to 9 range, that tells us that we have to have a contact time of 6 milligrams per liter. So minutes and milligrams per liter, or minutes and parts per million. So 1 milligram per liter times 6 minutes equals 6 minute milligram liters. So if you had a 1 milligram per liter residual, it would require 6 minutes of effective contact time before water reaches the first service connection. So it's important that we know what that number is before anybody has the opportunity to drink that water. So we look at this as a simple groundwater system with disinfection. So we've got our water comes out of the well, it goes through the pipe, chlorine's added, it goes through our entry point, or probably our last sampling tap before we leave. It's the entry point to the distribution system. And so it follows this path. So that denotes the time that we are concerned with that chlorine contacting the water. So it's a time from where it was the chlorine was added to where the first customer would have the opportunity to consume the water. So we're going to work through an example problem with contact time at the first connection. So in this example, a groundwater system needs to achieve a CT value of 6 milligram minutes per liter at the first service connection in the system. Now we've got 500 feet of 8-inch pipe between the point where we add that disinfectant to the point where that first service connection is. Okay, and the flow in that pipe is 250 gallons per minute. The free chlorine residual is 1.5 milligrams per liter. So our first step is, and we did these things yesterday, is to convert from gallons per minute to cubic feet per second. So if we divide it by 7.48, it gives us, dividing by 7.48 gives us cubic feet, dividing by 60 gives us flow in a second. So here we go. So 250 gallons per minute divided by 7.48 gallons per cubic foot, divided by 60 seconds per minute. We get rid of our minutes. We get rid of our gallons, and we end up with 0.557 cubic feet per second. Now, we're working we're working in cubic feet per second, so we want to divide our pipe diameter so that we get that go from inches, or we get that from inches into feet, and in doing that, we get 0.67 foot of diameter. Now we use our equation to figure out the area. We use a 0.785 times the diameter of 0.67 times the diameter of 0.67. You can see that's going to be in square feet, 0.35 square feet to be exact. Now we divide the flow that we had in CFS by the area, and that's going to give us a velocity. So if we remember, our flow equals area times velocity, and if we so we can divide to get our velocity, we divide our flow by our area, and that gives us 1.59 feet per second. And then we divide the linear foot of the pipe by the velocity to find out what is our contact time. So we know that we've got 500 feet that it's going to travel, and then for every second it's going to travel 1.59 feet. That means that if we divide our 1.59 into 500, that's going to give us the number of seconds that water is in that it takes to travel through that pipe. So we do that, we come up with 314 and a half seconds. Okay, so our contact time is, we're concerned about how many minutes it is. So we need to convert that. We'll simply divide the 314 and a half by 60, and that will give us the number of minutes that we have. And then we compare that to what we're given, right? So we're going to take our 5.24 minutes, the time that we have, we're going to multiply that by the concentration of the chlorine residual, and that'll give us our milligram minutes per liter. and it's 7.86. So our 7.86 is greater than our 6 that we were required to have, which means that we have achieved compliance. So let's move on to, what do you do when you want to disinfect a water main? So when it comes to disinfecting water main, I recommend that people look to the AWWA standards, because they've got methods for disinfecting water main and storage tanks and wells. So we'll provide some general information here, but when it comes down to it, I truly recommend that people look at those sources for some really good information as to how to do it. So after main repair, a low pressure event, or coliform contamination, water mains should be flushed, then disinfected. So if you've had an issue, you need to make sure that that everything's cleaned up. One other thing that you might consider with this, if you've had repair a low pressure event, you've had coliform contamination, you may need to, or you may have already issued a boil water. Would definitely be in contact with your regulating agency. If you've got any of these issues, let them know so that they can assist you and they're aware of what's going on. So there's a few different methods that we can go through. There's a continuous feed method. So you add chlorinated water until you get at least a residual of 25 parts per million. And after 24 hours of contact time, there should be at least 10 milligrams per liter of free chlorine residual remaining. So that's an indication that it lets you know that you still have some left after 24 hours. That means that it should have done its job. Another method, like you might take the tablet method for smaller water mains, and you place chlorine tablets, the HTH, in those at each pipe joint. When you're installing it, you fill the water with main, you allow a 24-hour contact time that's going to allow those to dissolve, and then the chlorine can do its work. And then at the end of that time frame, once again, you should have at least a 25 part per million free chlorine residual. And then the final method that's used is the slug method. You put in a highly concentrated solution, somewhere around 300 milligrams per liter, and you push that through the main, and you have a shorter, because it's a higher concentration, you're allowed to have a shorter contact time. And this works particularly well for larger water mains. It's important to note that after you've gone through and you've got this highly chlorinated water, that you do dechlorinate. So you take the chlorine out and then you flush it to waste. It's important that it's dechlorinated. I think there's a lot of desire just to pump that water out onto the ground or put it into the sewer system, but water at even 5 parts per million of chlorine can be toxic to plants. If you've got that 300 milligram per liter water, and you put that into the sewer system, that's going to cause quite a bit. I mean, it's in effect probably going to disinfect the sewage in that line, and that slug of water going to the water treatment plant or the lagoon would really upset their processes. So this table is beneficial for showing how to dose for with HTH or calcium hypochlorite tablets. If we take, for instance, an 8-inch diameter main and our pipe length of 20 foot, it tells us that we should be looking to apply 2 tablets in that water main to obtain our dosage. So there's little tables out there to help with how much to use. And all right, so emergency. Sorry about that. It's somehow that slide got pushed up. the text on that. So emergency disinfection of storage tanks. So I had mentioned that AWWA has these standards out there. In the case of disinfection of storage tanks, I recommend you look at AWWA 650 C60 C652-19. Usually the dash signifies the dates, because these things get updated, the dates will change. It's always important to go to find the latest version as they make changes. But basically, before disinfecting the storage tank, you should make sure that it's thoroughly cleaned out. You want to get out any sediment or anything that might have any biofilm, anything like that. In this case, you're going to spray the interior surfaces of the tank with 200 milligram per liter solution, a high chlorine solution, and you let it sit for 3 hours. You would rinse down the tank walls and drain out and once again dechlorinate the rinse water to make sure that you're not causing any harm to the environment when you discharge that. Next, you would look to refill the tank with clean water, and you're going to need to take the necessary bacteriological samples to ensure that you don't have any total coliform positive results before you're able to put it back online. And the next thing that we would quite often look to disinfect in general, once again, this is, I would recommend that you look to the AWWA standard for a full description of how to go about doing this. But for wells, you can disinfect with a dose that results in the end with a free chlorine of 50 milligrams per liter, and that needs to be maintained throughout a 24-hour period. So as you can imagine, with a well, you're looking at disinfecting this area where the water is. Quite often you don't have the area that you don't want to chlorinate an area where there's no water. So we're looking at dosing for the area that we actually have water in the well, that water column. And we can calculate the volume of the water in the casing in million gallons. And we can calculate the gallons of sodium hypochlorite or liquid chlorine needed for our dose, which we would have just above 50 parts per million to account. We got to make sure we account for those reducing compounds and the chlorine decay. So after that 24 hours, the chlorine levels will dissipate. So we take both of those things into consideration. And at the end of the disinfection period, we're gonna turn that pump on. We're gonna flush that water out and dechlorinate it and send that to waste as well. Now, after you get that water fully flushed out, obviously you're not going to want to have any chlorine remaining in the water. You would take a test of that, of the raw water without chlorine, and see if you've got negative bac T samples. So we can go through and we can run the numbers on disinfecting a well. So a well casing has a 10-inch diameter. It's a 10-inch diameter casing, total water column of 200 feet. Calculate the gallons of 12.5% liquid chlorine needed for a dose of 75 parts per million. And we're going to use a specific gravity of 1.2 for the liquid chlorine. So there's our well casing. It's 200 feet long. It's a 10-inch well. All right, so what's the volume? We go back to our volume of a cylinder, and we're going to start by converting. We need to find our volume. We're going to convert our 10 inches over to feet, divide that by 12, gives us 0.833 feet. So so now if we want to determine excuse me. So we take our area, we're going to multiply that by, which is 0.785 times 0.833 times 0.833 times the length or height of this casing, which is 200 feet. And we're going to multiply that by the number of gallons per cubic feet to get rid of our feet and get it in gallons, go through those steps, and we end up with just under 815 gallons in that 200-foot casing that's 10 inches in diameter. So now their next step, we're going to convert that into million gallons, and we can do that by dividing our 815 gallons by million gallons per a million gallons, which is the same as dividing by 1. It just allows us to move our decimals over, and it gives us 0.000815 million gallons. So now we can take that and we can do we can enter that in, and we put that, we multiply by our number of gallons by the dose that we need of 75 parts per million. We multiply that by the 8.34 pounds per gallon. We divide all of this. In this case, it's 12.5%, which works out to 0.125% liquid chlorine. We multiply by the specific gravity of 1.2, and we multiply that by the weight of water in pounds per gallon. As I said before, this is equal to 10. So if you wanted to, you could throw that in there. You're going to get pretty much the same answer, 0.408 gallons. Okay. So next topic we're going to cover, we're going to discuss disinfection byproducts. Okay. This is an important thing in this process of chlorinating. Unfortunately, we end up with these byproducts, which can cause some health concerns. And how do they form? So typically in groundwater systems, you have less concerns with disinfection byproducts, and mainly because you don't have the organics. So in this example, we're using a treated surface water, or we're treating surface water. The rainfall carries the organics across the ground surface and into our reservoir. We pump that water up the reservoir, and it goes through a filtration process, which pulls, the vast majority of the organics out. There's always a little bit that sneaks past. And so after we go through our other treatments, then we add chlorine, because we want to make sure that we end up with a residual out in the distribution system. But that chlorine reacts with those organics, and it forms these disinfection byproducts. And unfortunately, the disinfection byproducts end up going out into the distribution system, and through things as time and the chlorine residuals will continue to form disinfection byproducts out in the system. So the process of forming them does not just start where we apply the chlorine, but through time it continues. So what are disinfection byproducts? So disinfection byproducts are made up of two things, the two categories. And the first is the total trihalomethanes, or TTHMs, as they're called. So we've got these 4 chemicals: chloroform, bromodichloromethane, dibromochloromethane, and bromoform. And those 4 make up the THMs. Now, these 4 are volatile organic compounds that we find in drinking water. The concern is they are a cancer risk if they're at elevated levels. And so EPA established a maximum contaminant level for THMs of 0.80 milligrams per liter. Now, the other part of, I guess we'll cover. So as we had said before, that they're formed when they encounter organics. And so it's the reaction between the chlorine and the naturally occurring matter, or NOM, that forms them. And then the other side, as I jumped ahead, of disinfection byproducts are the haloacetic acids. And they call them HAA5s because there's 5 different acids that make up the HAAs. As you can see, there's monochloroacetic, di, tri, bromo, and dibromo. Those 5 make up the haloacetic acids. And haloacetic acids they're a weak acid. And once again, the concern is that they can pose a cancer risk. And EPA has determined that maximum contaminant level for those is 0.60 parts per million. And once again, just like THMs, they're formed as a result of reactions with those naturally occurring organic matters. And when we have the decay of plant and animal materials. So how do we prevent THMs, TTHMs, and HA5s from occurring? So we can do things with our storage tanks. We can do things to try and make sure that we don't have dead spots, so that the water that comes in doesn't sit in there for extended periods of time. Make sure that our turnovers are limited. So the idea of a tank turnover is that it's how long does it take for all of that water to get out of the tank? The stuff that comes in today, how many days is it going to sit in that tank before it actually leaves? So we want to reduce those numbers. You could also use chloramines as a disinfectant residual. So chloramines are less likely to form these THMs and HAAs, but much like anything else, there's no silver bullet. We're going to have things. Chloramines cause their own issues. And as we had said before, they can be the things that cause some of the taste and odor concerns. So another thing we can do is first of all, we say gently flush dead ends, and high retention being areas that water sits for long periods. But ideally, if we can get rid of dead ends, then we don't have to worry about flushing them. So minimizing dead ends is another thing that we can do here. And then if we regularly clean our tanks, removing the sediment and flush water mains as well to remove any debris, all that sediment and debris has the potential to have and harbor naturally occurring matter. And so if we can get it out of the system, then hopefully we're less likely to form those THM and HAs. And here's an EPA guidance manual. I highly recommend that if you're interested in this stuff, you check it out. These EPA puts out some really good guidance manuals that can help. They really condense and put the information that you might be looking for right into a document that's easy to read and very helpful. So we talked about this idea. We were talking about water age and the time that water might be in a storage tank or in the distribution system. Where do we have higher retention times? What are the areas that we might expect this to be a problem? Well, large diameter mains are one. So because they're big, there's more water in them, and they're almost like a storage tank to some extent. They can be, especially if they were over designed, or maybe things changed and they were properly designed, but now we have less water use in that particular area. Any mains that serve areas with low usage. So I look at this and I'm like, okay, well, why would you have a main that serves low, that has low usage? It doesn't serve very much. And it could be a factory was located in a location, and the mains were properly sized and they had a lot of use, and then that factory went away. Dead ends, that's usually for some reason or other, looping was not an option, and so We extended water where there's only one customer and they're way out at the end of the system, that type of thing. Seasonal things, you've got a park that an RV park that uses a bunch of water in the summer, but throughout the rest of the year, they don't use much. So that might affect that. And then finally, short circuiting. So the water has two different routes to get to someplace, and it always goes the same route. So the water, on the other side of the circle or whatever doesn't get used, or you can have short circuiting within a tank itself. We'll talk further about that, I believe. Nitrification is another topic. So nitrification it's a microbial process where ammonia oxidizing bacteria convert ammonia into nitrite. So that nitrite is then oxidized to nitrate by nitrate oxidizing bacteria. So what are the impacts of nitrification? You end up with high nitrate levels. You've got a loss of disinfection residual, so that's not a good thing. And then you have bacterial growth. So all those are definitely things we don't want to have happening in our distribution system. Factors that can lead to nitrification. Once I had said, we could have used, to avoid THMs and HAAs, those disinfection byproducts, we could use chloramines. But now chloramines have the potential to lead to nitrification. And ammonia, in this case, it's a food source for bacteria. That's not good. Warmer temperatures can lead to nitrification as well. Sediments out in the system that hold bacteria, they can lead to nitrification. So, a significant drop in pH and alkalinity can have effects with nitrification. How do we solve those problems? We increase the disinfection residual, and we have proper tank mixing and cycling. So once again, it comes back to that idea that we don't want to have the water that stays in the tank. It gets short-circuited, it ages, and as a result, you're probably going to see less disinfection residual in that water. And then tank cleaning. So we clean if we clean those sources of the sediments that harbor bacteria, if we take that stuff out, then hopefully we can solve the problem of nitrification. So we're on to dead ends now. We had talked about dead ends, and ideally systems don't have them, but historically, quite often we're dealing with something that if we had just installed the system today, we might do it differently, but this is what we had. It's been in place for years, and we have to deal with what we have. So what are the problems with dead ends? So dead ends are going to see a higher water age. So because the water doesn't flow, if you got low use at the end of a dead end, that water is going to sit there, and it's going to become old. And as water sits, we know that chlorine residual decreases. You're also going to have, because the water's not flowing, it's going to allow any sediment to drop out in the pipe. Also, with lower chlorine residuals and lower flows, we're going to see an increase in biofilm growth. Scale will be allowed to form as that same water sits in the pipe. The scales can build up, and we're going to have an increase in DBPs. Disinfection byproducts will increase in dead end areas. So these are the areas that we're looking at as considered to be dead ends. I would consider a lot of this to be dead ends in this scenario. There's an example. Maybe there's a plant at the end of that that helps keep that dead end from being an issue. So there's a study done that found that distribution systems that have dead ends with free chlorine residuals less than 0.2 parts per million, or chloramine levels less than a half a part per million, had substantially more coliform occurrences system-wide than systems maintaining higher residuals. So, this just points to the fact that we want to keep those residuals up, especially if we have dead ends. What are the effects of increased water age? So there's another study, the effects of residence time to water quality in large water distribution systems, that was done in 2013. Excuse me, and in that study, the researchers found that the areas with low velocities, they had issues both with heterotrophic plate bacterial growth, and the levels of THMs continued to increase with water age, regardless of the presence of normal chlorine residual levels. So it became a problem both that even normal chlorine residuals couldn't solve, and chlorine residuals decreased with water age. That's something we'd normally expect. Once again, the HPC numbers, that estimates the number of bacteria, yeasts, and molds that might be in there. So it's not just bacteria. And with this HPC, they're noted in colony forming units per milliliter. So we look here, and as the retention time increased, we saw an increase in the formation of these HPCs. So this chart is simply, it helps to show what happens through time with both THMs and with chlorine residuals. So if we look at this as time goes on, our chlorine residuals will drop. So in this case, we were at, say, just over 5, and now we're down to just over 1. So we've seen a significant decrease in chlorine residuals. But in the same time, we've seen an increase in the THM levels. So it's just time in a distribution system, chlorine residuals decrease and THMs increase. So what's the benefit of storage tank turnover? What is storage tank turnover? And so that's the idea that I mentioned before, where we're gonna replace the water that's in the tank with fresh water. The water that's in the tank leaves the tank. And that's the time where it takes all of the water to be exchanged. So for best operations, we want that turnover to be less than 5 days. So we can keep that chlorine residual up and keep that water moving. It's less likely to cause this issues. But as we've talked about in other instances, there's a balance. We can't have this enormous tank because we want to we need so much money for peak flows and higher usage times. But we need to minimize our age and our turnover, make sure that we have turnover. So it's a balancing act to have the right size tank. And in some instances, you'll have operations of storage tanks where at different times of the year they have less, they use less of the tank, just to make sure that they have the proper exchange. So let's see, we've got a 500,000 gallon storage tank. It receives an average flow of 175,000 gallons a day. What's the turnover for the tank in days? So this is under the assumption that all the water that goes in comes out. There's no short circuiting. So we convert the 500,000 gallons to gallons. So 500,000 gallons is 500,000 gallons. We divide the volume by the flow. So we divide that 500,000 gallons by 175,000 gallons a day. And that tells us that it takes 2.86 days For the water that enters today, it'll be 2.68 day or 2.86 days before that water leaves the tank. So short circuiting and tank mixers. So as we can see, what happens is that water, the lighter, warmer water, the warmer water tends to be lighter and it'll sit on the top, and the colder water is heavier and sits on the bottom. I'm sure that most people have seen that if they've ever jumped in a lake in the summer. That surface water, the stuff at the top is warm, and down below it's cooler. And it tends to stratify in different layers. So if we have our inlet to our tank at the top, and we have our outlet at the bottom, the water that comes in is typically colder. Water entering is usually colder than the water that's in the tank. So in theory, what would seem like it should happen is that water would then drop to the bottom, and the water that's coming in is going to be the cold water, so it's likely to be the water that leaves first. So that's the idea of short circuiting. It doesn't spend, this water entering doesn't spend its time in the tank. It just goes right through. So that means this water at the top, the lighter, warmer water is probably going to stay. So that's short circuiting, and then mixing can be done with a multitude different ways. We look here, and you can add air that can move the water around. You can have it enter so that it circulates. These are all good ways to ensure that we don't have stagnant water or water that sits. The water gets mixed, so it's overall better. So let's look at now at the effects of disinfection on biofilm. So, and what its relationships are to DBPs, disinfection byproducts. So, we can't have one thing, we got to balance everything. So if we look at our pipe, we've got, we've got naturally occurring organic matter. It comes in, it combines with the chlorine, and we create disinfection byproducts. So we've got biomass, and that becomes detached. It reacts with the chlorine, and it creates disinfection byproducts. We know that chlorine can reduce that biofilm growth rate, and it can even destroy biofilms. But it does create disinfection byproducts. So there's a recent study out where they observed low disinfection byproduct formation with a chlorine residual of 0.5 part per million. When they increased the chlorine residual to 2 parts per million, those DBP concentrations went up and then eventually decreased over a time of about 2 years. So what happened to cause that? So they believe that when the free chlorine at 2 parts per million was, it was effective at getting into this extracellular polymeric substance, this layer. There's a layer on the outside of the biofilm. So it was able to penetrate into that. And that led to this initial time where we saw an increase in disinfection byproducts. But as it broke through there and got rid of the biofilm, the thought is that that water gets removed, it gets used, goes through the system, and then now we're in a better spot because we've gotten rid of the biofilm, and we went through our little spot where we had elevated DBPs, and now we're good. Okay, so how does pipe material, and how do we work with different pipe materials and controlling biofilms? So let's first look at PVC water mains. All right, so in PVC water mains, chlorine achieves greater levels of inactivation in biofilms than chloramine. So for PVC, we would assume that that chlorine is better than chloramine. So a concentration of a part per million of either free chlorine or chloramine has been shown to reduce HPC counts and coliform counts by more than 2 log in biofilms. So that magic number of 1 part per million. Now in iron water mains, so Greg showed you before the slide with the tuberculated cast iron water main, the inside of that. Quite often we see a higher chlorine demand based off the sediments and the tuberculation. Free chlorine residuals as high as 4 parts per million have shown to be ineffective for iron water mains. So that tells us that even at really high levels, it doesn't always, chlorine doesn't always do the greatest job on those biofilms. And then monochloramine residuals greater than 2 parts per million have been shown to be successful at reducing. So it depends on what we have. That what we have determines quite often what we need to do. So we're on to poll number 3. We'll do this poll and we'll take a 10-minute break. And what the poll is, we'll let you do the poll, respond to the poll during the break. What are factors that can lead to increased DBP production and loss of residual? Is it A, tank turnover less than 5 days and excessive flushing? Is it B, tank turnover greater than 5 days and sediment buildup? Is it C, use of chloramines and flushing and system flushing, or is it D, all of the above? So Lori, if you set a 10-minute counter, we'll take a break and we'll come back and respond to the poll questions.
Okay, thanks, Daryl. 10-minute timer set.
All right, we are back. We'll end the poll here and share the results with you. So 77% of the people said B, tank turnover greater than 5 days and sediment buildup. All of the above at 19% and C at 4%. Nobody said A. So let's look at this. And the answer is B, tank turnover greater than 5 days and sediment buildup. Those are all bad things as far as DBP production. Tank turnover less than 5 days, as we said, was something we were looking for. Excessive flushing obviously is going to keep our water fresh. And then use of chloramines in system flushing should not add to DBP production. All right. So how does so we've got to look at disinfection and biofilm study findings. So there's been some studies done regarding disinfection and biofilm, and one of them done in 2002 looked at free chlorine followed by chloramines as being the most effective disinfection strategy to reduce biofilms. And that all sounds great, but we start adding now we're dealing with free chlorines and chloramines. I would imagine that the regulators are going to require you to do the necessary testing for both of those. It just becomes pretty burdensome. Flushing followed by disinfection is the most effective sequence. So if we're gonna do this, we're best off to do our high velocity flushing first and then disinfect afterwards. And just a word of warning, if you're going to change any of your treatment processes at all, including disinfection, you need to thoroughly investigate and pilot test it. I would think that the state regulators would look at that and say that that's it's a change in treatment. So you'd also have to get it okayed by them, potentially get a permit to do that. So here's another one of those good EPA guidance manuals. I encourage you, if you're interested in disinfection profiling and benchmarking, that you look at that. So now we're going to move on to sanitary surveys. It's quite often one of the scary things, I think, for water system operators is the idea that regulators are going to come out and they're going to do a survey of your system. I would hope that that's not the case, that you have no real reason to be concerned. The reason is that they're out there and they're doing these is they want to identify if there's any potential problems, any risk to public health. They want to make sure that your system is able, that has a capacity to provide safe drinking water to its consumers. And it's an opportunity for some education and technical assistance. It gives the regulators an opportunity to see everything that's going on in the system. And hopefully they can provide some tidbits of knowledge and assist you in any issues that or concerns that you might have. It's an inspection of the entire water system. We're going to look at all sorts of things when we come out to do a sanitary survey. Why do we do it? Safe Drinking Water Act requires it. For surface water treatment systems, it's under the interim enhanced surface water treatment rule. For groundwater systems, it's required under the groundwater rule. And community water systems are required to have a sanitary survey done every 3 years, and the non-community water systems are required every 5. So what different things do we look at when we look at when a sanitary survey is conducted by a regulator? So we're going to look at the water source. We're going to look at the different treatment processes. We're going to look at the entire distribution system, including the finished water storage. We're going to look at the pumping and controls. We're going to look at the monitoring and reporting that's done by the system. What sampling they are doing and how are they reporting it. We're looking at the system management and operations. How is that system run? And then we're also going to look at operator compliance. So that includes having the properly properly licensed operators, having enough operators, and things of that nature. So we're going all the way from source through the whole distribution system, including these other items. So what are the processes? What can you expect if you're going to have if your state primacy agency is coming out to do a sanitary survey? So first of all, I would encourage you to make sure that all your records, anything that they might be looking for, are readily available so that you can show them to them when they come out. Need to be prepared to give a tour of your system. If you've got a treatment plant or a well house, I would expect they'd want to see those. If you've got storage tanks in the system, they'd probably want to look to the extent that they can at those. And then after the survey, you can expect that they'll provide you with a detailed letter that shows if there's, whatever their findings are, any recommendations they have. If there's sanitary deficiencies, they're going to list those as well. And they're also going to tell you, what time frame they expect you to correct those deficiencies. So there's 3 different categories of deficiencies. So we start with the significant deficiencies, which is the most important ones. Those are problems that could cause public health concerns. They could introduce contamination. Moderate ones, they could lead to problems if you don't address them, but there's nothing really immediate. And then minor are those things that usually would be helpful to know to aid you in operating your system and making it work the most efficient. So let's look at water source. So, and these are all examples we see here of well casings, and but we're looking at to make sure that you've got a proper wellhead construction. In this case, wells aren't located too close to water bodies or contamination sources. Do you have a good source protection program? This photo shows the cap is broken on this well casing. Obviously, it allows all sorts of things to get in there. The next one, the casing doesn't extend the proper height. The recommendation for casings above ground are determined by the state well construction standards, but typically it's a minimum of 18 inches above grade is required. And in this last one, obviously this well's got standing ponding water here. It's very close to a water source, so it's that type of well would be difficult to isolate to be certain that we're not influenced by this water body as well. For treatment things, we're going to look at all sorts of the different treatment processes. We need to make sure that you've got points for you have to be able to add your chemical. You got to be able to collect samples. You need to store your chemicals. You need to use the proper NSF approved chemicals. And then if you look at this, both of these photos show the potential for backflow issues. Here we've got something that's piped directly into the drain. It doesn't show where that pipe comes from. In this case, it appears as if we have in this photo that there's 2 chemicals that are placed at the same point. It's possible for them to backflow. You could put one chemical into the other and they may not be compatible that way. So there's a lot of different things that can be looked at. One issue that I personally was involved with was an issue that with the filling of a day tank, and it resulted in a chemical being overfilled in that day tank, and ended up the chemical went into the wet well, went through the treatment process. Those are the type of things that hopefully are avoidable. This is information that the regulator might be able to identify and help you with. In that case, they ended up installing a dead man switch so that the operator could no longer walk away and have that pump operating. He had to stay until it was until the tank was full, so it only operated when he was there. There's a lot of things that can be beneficial that can come out of these sanitary surveys. As I said, any chemicals need to be NSF approved and properly stored. In the distribution system, we're going to look at the entire thing. Do you have a lot of dead ends? Do you, do you have cast iron pipes? Do you have typically have a lot of main breaks? Is there need to replace infrastructure? Do you have a cross connection control program, and are you following that? Are you performing those inspections? Do your valves and hydrants work properly? Are you exercising your valves? Are you flushing your hydrants? Are you doing routine maintenance on those hydrants? Do you have proper flows? Is there any issues? What is your leakage? If you compare the amount of water that you pump from your wells compared to what you sell, are those numbers in line? This is a very obvious one, a broken fire hydrant. I don't imagine that I'd ever see that when I was doing a sanitary survey, because I think people typically pick those up and so you wouldn't leave that there. And then, finished water storage, so our storage tanks. With this, we're going to look to evaluate the conditions that we can. I know one of the issues that we had is we weren't allowed to climb elevated storage tanks. So we relied on things like tank inspection and cleaning reports to show pictures. We'd relied on operators to tell us whether, if there's a gasket on a hatch, things like that, things in areas that we couldn't see. So quite often what I believe regulators look at when they look at storage tanks are these issues. They're unprotected. The photos show unprotected openings in the top of a storage tank. If you can happen to look in, are the screens damaged on overflow pipes, and do they have the proper mesh on tank vent screens? To keep out the bugs and things that you could have hornets and wasps and things that can build nests up in these things. And so that's why you got to have the proper screens. So you look at the pumps, make sure that you're providing proper maintenance on the pumps, that they work properly, and that you have redundancy. It's important that you have more than one pump, because if that pump fails, if you only have one and it fails, you're not going to be able to provide necessary water for your consumers. The photo on the bottom right shows a flooded pump meter pit. Obviously, that's not a good thing, because typically these meters and valves, meters were probably not designed to work underwater, at least not for significant periods of time. It would probably cause valves and meters to corrode and rust prematurely. You would hope there weren't any leaks in that, but if there were, now you're subject to potential backflow. So these are all a number of reasons why you wouldn't want to have that type of situation. So we said, you're going to have firm capacity of your pumps, redundancy. You don't want pumps that cycle too frequently, because that can cause to wear, temperature issues. You need to have proper screening on your pumps to make sure that you're not that's not a safety issue. Is there any histories of outages or low pressures in your system? And then on to operator compliance. So with operator compliance, you want to make sure that they've got properly licensed operators, that those operators are receiving the training that they need. so that they can manage and maintain the water system. So states will quite often have operator certifications that are dependent or required based off the type of treatment or distribution system, quite often based off the size within those classifications. And then do you have enough staff to operate and maintain the system? If you're required to have 24-hour-a-day operations, do you have enough staff to run the plant 24 hours a day? And then to operate the system, you need to undergo training. Most operator certification programs in states require continuing education credits or hours or whatever the term may be, but in order to renew those licenses. So are you receiving the proper training? And do you have documentation of such? Management and operations is a lot of that's the paperwork stuff. Most of the in the field, in the plant operators don't end up having to deal with this, but we'll look at those type of things, your record keeping, your planning type stuff. Do you have the policies and ordinances in place that are necessarily and allow you to properly operate the system? Do you have the finances set up? Do you have, are your rates such that you can maintain the system and provide for capital improvements? What's your system service area? Where do you serve? Are you doing asset management planning so you know what needs to be replaced, what your priorities are, and have you done an emergency response plan? Proper public notification, including the consumer confidence report. That's probably the most obvious, but also if you have a violation of any sort, monitoring or reporting violation that you have to notify the public about. And then once again, cross connection control records and your program. Typically, they would like you to have available any of the previous sanitary surveys, and that would quite often be based off a record retention requirement. And then the same with permits. If the regulatory agency issued permits to you, do you have those on file if they were to ask for them? And some of the more common problems that are found are to have, quite often systems will have an emergency response plan, but it's not up to date. Operators change, contractors change, that type of thing. And as I had said, do you have the financial situation? Do you have the rates and the money set aside to make sure that you can operate the system and that you can provide money that there's money available to do any necessary repairs, and that the system components get replaced as needed. Monitoring and reporting looks at all sorts of the testing and sampling and how you report that stuff to the regulatory agency. It involves your sampling plans. There's a multitude of different sampling plans that you might have to look at, whether it's the bacteriological sampling site plan, disinfection byproduct plan, lead copper rule sampling and plans. What kind of water quality are you testing? Or what's necessary? A complete treatment system, surface water system is going to require a great deal of water quality information. And how do you control your processes to make sure that you're meeting your required? If it's a surface water treatment plant, are you meeting your turbidity levels? Compliance monitoring results, just your bacteria results, your disinfection byproduct results, those type of things, and what kind of records you keep of that stuff. We mentioned disinfection residual monitoring. Are you using using approved laboratories? So a lot of the required compliance monitoring, the tests have to be done by certified laboratories. And what procedures are you using to collect your samples? All right, so I wanted to poll number 4. Which of the following do you think is a tier 1 sanitary deficiency? If you remember back, tier 1 is the most serious sanitary deficiency. So is that a water operator has not attended a training in the last 10 months? The end of a tank overflow pipe is 20 inches from the concrete pad. A well casing does not have a sanitary seal, or the system is understaffed. We get up to a certain percentage, we get a good deal of these coming in, and we will end the poll. Okay, it looks like we've got 77% of 79% of the people have responded. So I'm going to end the poll, and I will share with the results with you all. It looks like 85% of the people have indicated that they think it's a well casing that does not have a sanitary seal. 14% said the system's understaffed, and 2% said the end of a tank overflow pipe is 20 inches from the concrete pad. And so, yeah, I mean, all of these things could be issues. I think that the one issue, the one that's the most serious is a well casing does not have a sanitary seal. So that's important because it could allow contaminants to enter the well, and which could directly result in a public health concern. Okay, so we're under our last topic, sampling and monitoring. Let's look at so why do we monitor chlorine results? There's a few different reasons that it's important to monitor chlorine results or residuals, excuse me. But if we look at this pipe, we've got a lot of things going on here. Let's see if I can. So, we've got all this, we've got water coming. It's not just simply water coming in and water going out. We've got this biofilm, we've got deposits, we got all this stuff going on. And so when we're applying chlorine, we're required to keep our residual disinfection level to below 4 parts per million. So if we don't do any monitoring, if we don't take any samples, we'll never know if we're below that. The other thing is that we want to do it from an operational standpoint because we want to make sure that we have at least 0.2 parts per million of chlorine if that's what we're applying, or 0.5 part per million of chloramine. So this ensures that we have protection against those pathogens. So we're keeping our residuals up. If we don't monitor, we don't know if we have that. We're also going to inhibit or try to reduce or slow down the growth of biofilm, which is an important thing because as we indicated, that can end up in causing bacterial issues. It can cause issues with disinfection byproducts. And also, this is an early warning sign. So if we have typically have a chlorine residual consistently out in our system, we're still applying at the same rate, and then all of a sudden we see that that residual has gone down, then that means that there's something that's in the system that's taking up that chlorine. And then once again, ensuring that we have that minimum recommended residual, especially in those areas that have dead ends. So how do we go about monitoring our chlorine disinfection residuals? So most commonly people use the DPD method. So the DPD method is we take this long named chemical and we use it as a reagent. So we take a vial of our water, we put this reagent in it, and it if there's chlorine around, it'll come to a certain color, a level of color, and typically in a pink to red solution. We can use a free residual test for chlorine, or we can do a total residual test that will indicate our chloramine. So if you look at these vials, it goes anywhere from, this is what it might look like if there was no chlorine in that sample, to low chlorine, to high chlorine, always also to the point where we've got so much chlorine in the water that it kind of even bleaches out the color. So this photo shows a vial of our water where we're adding in the DPD and these little pillow packs. The next shows what might be some chlorine. Obviously, we see the pink color. There's chlorine in that sample. We take that vial with the water and our DPD in it. We put it in our meter, and it gives us a reading. And this is what they call a color wheel, and so this color wheel is kind of an old. It's the way we did it for the longest time. So that is a comparison. You take a sample of the water in a vial that you don't add the DPD to, and then you take a vial that has the DPD, and you put it into this thing, and you compare the colors. So where it falls on that dial indicates how much chlorine is in. And it's kind of funny, these things are sensitive to light. Through time and light, the colors will dim. And so what was a dark or bright pink will then fade in color. So quite often guys out in the field will take these things and they throw them on the dash of their truck, and they sit in the sun and they fade out, and all of a sudden their chlorine residuals are higher than they actually think they are. So I've mentioned that, through time and temperature, that chlorine the residuals decrease, and that's to be expected. But we hope that chlorine residual lasts, for a few days and hopefully for up to a couple of weeks. So we look at this as a study that showed some chlorine residuals and how they were affected by months and how they decreased. And if you look in this scenario, we want to maintain about 0.2 parts per million. Well, it was about 7 hours that it took for that to reduce down to that 0.2. And this was a study done in Chile that showed a rapid decay. So 7 hours is really short time frame for chlorine residual to drop that much. There's a link at the bottom of this that shows where you could find that. The demand, how do we keep the demand down so that we can reduce our residual decay? Flushing at scouring velocities, keeping our storage tanks cleaned out from any sediment, and then cast iron pipes with quite often have a major effect on chlorine residuals. So if you've got them, if you're not going to replace them and you could line them, that would also help. And our water age, to keep that water fresh so we're not out here extended amounts of time, can be done by flushing and making sure that we're either mixing in our storage tanks or we're not short circuiting. So this is this shows the chlorine residuals and how they decay on a mapping system. So the darker areas to the left are where the higher chlorine residuals are. That's the source of that's where we're getting our water from. And it shows that as we get farther away and we get to these dead ends specifically, our chlorine residuals decrease through time. So we had 1 part per million entering the system. Here at this dead end at the top, these 2 dead ends, we were down to 0.01 and 0.05 respectively. So even though we had that coming in at 1 part per million, those areas decreased considerably below what we were looking for at 0.2 parts per million. And they did this study because they were looking at the idea of booster disinfection locations. So we've got low chlorine out in the distribution system. Is it beneficial to have a point where we add chlorine and boost to get more chlorine out there? Obviously, that brings about concerns with disinfection byproducts, because once again, we're adding chlorine to the system, and any of those organics that still remain out there could cause those disinfection byproducts. Flushing can help, with residuals. We've said that over and over again. And there's always that case where maybe booster chlorination is effective. So we can also look at monitoring our pressure out in the system. It's important that we maintain at least that 20 psi at every point in the distribution system, because if we don't, there's always the potential for backflow or back siphonage into our system. It's important for maintaining fire flow. And you'll find, as we talked about, those cubes of water stacked on top of each other, the higher our system is, we're going to see reduced pressures because we have fewer cubes of water on top of that. So let's look at the total coliform rule. So the total coliform rule is that's our requirements to collect our BACT samples and our chlorine residuals out in the system. And those things are based off of 2 things. It's it's our population. And then there's 2 things that we really want to talk about. That's how we determine how many samples are required and what we do if we have a positive sample. So if we have a positive sample, and you're required then to take at least 3 repeat samples within 24 hours at the original routine site and within 5 service connections upstream and 5 service connections downstream. That's a minimum if you have a total coliform positive. So if you're a system where you only collect 1 routine sample per month, then you're going to be required to collect another sample. So you'll collect the original, the upstream, the downstream, and then another sample in the distribution system. And that location needs to be representative of your distribution system. So the other thing that's important to note is, as I said, the number of samples that you have to collect is based off your population. We'll show you a chart that indicates the populations and the number of samples that are required. But if you're a system that serves less than 4,900 people, you can collect routine samples all on the same day. Whereas the samples that are larger and required to collect more samples, they have to collect them throughout the month. So this takes a bit of the burden off of small systems, that they don't have to collect several times throughout the month and maybe have to take them to the laboratory or mail them out. So here's the link to that EPA guide. This is a very good one to have for if you're having questions about total coliform rule. Here's a chart that shows populations. We talk 4,900 or less. Those are 5 samples per month or less. They can do it at one time. Everybody that's larger and has to collect more samples has to do it multiple times throughout the system. So the revised total for coliform sampling, we go to our revised total coliform sampling site plan. And in that plan, we're going to identify the locations where we're going to collect our samples, our routine samples. And then also we're going to identify where we collect our repeat samples. So it identifies the routine sampling locations. It identifies the repeat sampling locations within 5 connections upstream and downstream. So each one of these, you'll note that this system is chosen January and April. Looks like every 3 months they go through, they'll sample one location first, a second, a third, and then they start back over. So they do these 3 samples and they do or 3 sample locations and they do them 1 sample per month for a quarter. So for each one, they've identified their repeat sample locations, and it's important that those sample locations are representative of the system. So you can't bias it towards a certain area. You need to look at your system as a whole. If you're a system that's predominantly made up of residential, and you've only got a couple of commercial customers, it doesn't really make sense that you would use the multiple samples in that commercial district. You'd want to be able to spread those out through your residential areas. You also need, if you have different pressure zones, then those definitely need to be considered, because with pressure zones, the water doesn't really go between pressure zones. So each one should be looked at individually. You've got significantly different geographical areas. If you've got, you serve 2 sides of a river and maybe there's only 1 or 2 river crossings, you should have sampling on both sides, things of that nature. And then if you've got different sources, if you've got wells that serve predominantly different areas of the system, then you should look at those as locations. So we're going to look at this in more detail. We'll look at this 1, 2, 3 group drive. We'll look at this we'll show, does this meet the requirements? So our initial from our plan, this is our routine site is 1, 2, 3. And so if we're going to look at our downstream sites, we need to be within 5 service connections. So if this is our routine, we've got 1, 2, 3, 4, 5. This 5th site just makes it. So this is within 5 service connections downstream. And if we look at the upstream, we've got 1, 2, 3, 4. It's at the 5th site. So both of these meet the requirement. So sometimes it's hard to explain, what do you mean by within 5 service connections upstream and downstream? And sometimes it's hard to tell. If you've got a loop system, you may wonder, well, how do I know what's upstream and what's downstream? But if you're using this example, it really doesn't matter, because you're going to be within 5 in either direction. And so that will suffice. So let's look at how do we collect a coliform sample and what's the bottle look like. So you can look at this bottle, and it's a plastic bottle. It's got a seal around the cap, a plastic seal. It's also got this tablet in the bottom. That tablet is sodium thiosulfate, which is a dechlorinating agent. So if you look at the cap, it should be sealed. If not, use a different bottle. If you're collecting a sample and something goes wrong, throw it out and collect a different sample. It's really important that you get representative water that's representative of the water in your system, and that you don't cause a contamination where there wasn't one. So with that in mind, you want to take the cap off. You want to keep the cap down so that you don't want to flip it up so things could fall into it. You hold that lid or that cap down facing while you collect the sample. You want to fill, there's a line 100 milliliter line. You want to fill it to that line. And then when it's full to that line, then you replace the cap on there. And then there's this sodium thiosulfite tablet in the bottom. If it's missing that, then you shouldn't collect the sample as well. And then as far as where the location where you're going to collect the sample from, some of the important things is you want to avoid taps that have threaded spigots. So if it's got a hose bib on it, it's probably not good because that's a location where bacteria could be on the outside of the, not actually part of the water, but attached that faucet, and it could fall into your bottle and it could give you a false positive. You want to make sure that the tap is above the ground. Everything, the closer you get to the ground, the more likely that something splashed up there or something got into the tap. And you want to make sure that you run the water until it cools, to make sure that you got water that's not just sitting in the pipes, because that's not indicative of the water that's out in the distribution system. That's could be more indicative of your home. And if possible, you want to disinfect the water tap or the tap that you're using. You can use alcohol, you can use chlorine. You definitely want to wipe all that off before you collect a sample. And if it's designed properly, then you actually can torch it, which is probably one of the best ways to do it, because that will kill anything that's on the tap and should give you water that is representative of what's actually in the distribution system. Stainless steel gasketless valve is ideal. The turn down spigot and small diameter copper tubing, gooseneck copper tubing. Those are all great sampling taps. So we've got the total coliform rule. We've got the revised total coliform rule. And what's the difference? So E. coli was added as an MCL to the revised total coliform rule. And the idea is that we have a find and fix approach. So we're going to identify what caused that sanitary deficiency, what's caused the problem that led to the total coliform or E. coli positive. We're going to identify it and we're going to fix it. So there's a level 1 assessment and there's a level 2 assessment. And a level 1 assessment, that puts the onus on the utility. So the utility is required to investigate any sanitary deficiencies that contributed to a total to 2 or more total coliform positives in a month. And so that's for a system with less than 40 routine samples. So if you collect less than 40 in a month and 2 of those come back positive, then you've got to go through this process. Or if you're a larger sample who collects 40 or more routine samples, then if 5% of those are positive, you've got to go through the process. And then if you go through that process and you continue to have issues where you've had to do 2 level 1 assessments yourself within a 12-month period, or if you have an E. coli violation, then that's when the state regulatory agency is going to get involved and they're going to do their own investigation. So that's how this progresses. So, what are the concepts between the revised total coliform rule? So in order for there to be contamination, there's got to be a source. And then there's also needs to be a pathway or a way for that contamination to get into the system. There needs to be a mechanism that causes that contamination to enter the system. So we need to find out what those things are to correct it. There's a quick reference guide for that. The lead and copper rule is a little different. Some of the things with this go against the ideas that for coliform sampling, but the rule established action levels, and action levels are different than maximum contaminant levels. So the action level is based off the 90th percentile level of all the tap samples that are collected. So that 90th percentile, if you had 10 samples and you rated them from the lowest to the highest, your 90th percentile is going to be the value that was of the 9th highest sample. And that's both for lead and copper. That sample is a first draw, so it's different from our total coliforms in that we want to capture that water that's the first water out of the faucet, and the faucet also has to be not used for at least 6 hours. So there's a stagnation period there. Sampling is typically done every 6 months. If a system doesn't have any issues, quite often that will go to an annual sampling. It can be reduced, or if there's problems, it can be accelerated, go back to 6 months. So an action level exceedance is not a violation, but it can trigger you to have to do other things. You could have to do some water quality parameter monitoring out in your distribution system. You may have to do corrosion control treatment, a study to determine what's beneficial as far as, or if it's necessary to do corrosion control. You may need to monitor your source water or how you're treating your water. You may have to do public education. If you've got lead service lines, chances are you're going to be doing some lead service line replacement. Probably already doing that if you have them anyhow. So there's a link to the lead and copper rule, quick reference guide, and a link to the lead and copper rule revisions. Lead and copper sampling in tiers. So here's where we figure out how many samples we have to collect based off of our population. And they put them into these groupings of small, medium, and large systems based off of populations. The smallest system here, standard monitoring for lead and copper sampling sites, you'd have to have 5 sites under your regular routine, and then your reduced stays the same. You have to collect 1 water quality tap sample, and reduce stay the same. So as the systems get larger, they start to give you a little bit of a break. If you're doing well, the results are coming back good, you can reduce those with regulatory approval. You can reduce those sampling numbers down. Now, where do they want us to collect these samples? So the idea is it's single family first. So, and we want to we're trying to find the worst possible location. So EPA has deemed that the most likely to have copper are going to be single family homes with copper lead solder constructed between 83 and 88, lead pipes, including lead goosenecks or pigtails, or lead service lines. So those are our highest priorities. So if we have these, we have to use them. If you don't have enough of those, or you don't have any, then you can you can make those up with extending that to all building types. So it could be commercial or multifamily, but with the same criterias. And then if you use up all of those and you still need to collect samples, you look at tier 3, which are single family structures that have copper with lead solder constructed before 1983. And if you go through all your sites and you don't have any of these tiered, or you've taken what you can out of there, then you can go on to the other. And that's basically, you need to collect samples that are representative of your system. Now, under the disinfection byproduct rules, these identify the sampling requirements for those. And that's, as I said, that's based off a locational running annual average. Our THMs form when chlorine reacts with organic compounds in the water. We've already covered that. Now, bromate, if you're using ozone, then you would have to collect bromate samples, because ozone reacts with naturally occurring bromide in the water, and that can result in bromate formation in your distribution system. And then chlorite can form if you're using chlorine dioxide. That's where that reacts with organics and forms chlorite. So if you're using chlorine dioxide, you're going to have to collect chlorite samples. And this shows the quick reference guide for the disinfection byproduct rule. So what do we expect if we're going to have to do disinfection byproduct sampling? So once again, we've indicated the MCLs for both trihalomethanes and haloacetic acids. Our compliance is based off a locational running annual average. And you'll have to do an evaluation prior to determine what those sites are, where you're going to collect your samples. And they're typically the places where you have the most the longest retention times, and you're going to have to do it when the water is the warmest. So whatever the time of year that you have the warmest water, because those things are both indicators, or they result in THM and HA formations. HA sample bottles, glass bottle, there's a preservative in there, ammonium chloride. You want to make sure anytime that you have preservatives that you're using gloves and eye protection. Make sure you don't rinse that out of the bottle, because that's there as a preservative to keep the sample preserved till it gets run through the laboratory. In this case, you fill it up to about within 2 inches, or we would say the neck of the bottle. It's important for both of these that they're kept on ice. Temperature and time is very important, especially for the THM samples. In that case, we've got these bottles. They've got a plastic cap with what they call a rubber septum in there. They have a preservative in there as well. You don't want to spill that preservative, but when you fill these bottles, you want to make sure that there's a water meniscus that goes over the top of them. No air bubbles. You put the cap back on, and hopefully there's no air. You can turn it upside down. There should be no air in it. And there's possibly that even rubber septum will bubble up on it. And once again, time and temperature very sensitive. So quite often systems will take these directly to the laboratory the day that they collect the sample. And this shows the number and frequency of samples required for THM and HAAs. Important thing, subpart H, that's going to be your surface water system versus groundwater. So you can just look at here, if your groundwater system and you're between 500 and 10,000 people, you're required to collect samples annually, 1 per treatment plant or well. And then under stage 2, annually, 2 distribution system monitoring locations. So you have to collect 2 after the stage 2 went through. There are requirements to monitor the system for TOCs and alkalinity as well. Chain of custody, it's important. When you fill these out when you collect your samples, and you've got a bunch of information that you need to have: the sample identification, date, time collection, the people, or the sample source, preservatives, what you want to have it tested for. Each time it's transferred, it's signed off and dated and timed from person to person. Or what preservation and storage methods did you utilize? The lab that receives it's going to verify the chain of custody, record the dates, check to make sure that the samples weren't tampered with. And then a chain of custody is going to have to be maintained as part of the official record, along with any shipping receipts. So this is an example of a chain of custody. You can see the information, the company and address required, who did the sampling, they signed off on it, information about the sample, whether it's a grab or composite sample, different information, things there, what analyses you're asking for, and the total number of containers, the relinquish, that's where people sign off that they received it, date, time, stuff like that. Information about number of coolers, the temperature, stuff like that. I said a lot of these things are important to the times and temperatures. There's 3 different tiers of public notification. So the most important are tier 1. Those are situations that there's potential for human health issues. People could be immediately impacted, and they require that there's 24 hours of notification. The delivery methods are very prescriptive and required. You need to use all the methods possible at your disposal: television, radio, newspaper, notice in public places. If there's any other ways, social media in this day and age is another source, but it needs to be done quickly, and we need to notify the public of major issues. Tier two notifications are less stringent. They're less severe issues. You may have had an exceedance but it really wasn't that. It wasn't something that could cause immediate harm to human health. So with that, you may be allowed to notice through the media, through posting, or through the mail. And then the least serious one is a tier 3. It doesn't impact a drinking water standard. You're not violating a drinking water standard. Quite often, it's you failed to either take a required sample on time, or you failed to notify the regulatory agency of that. The requirements are similar to a tier 2, but quite often, because you can wait up to a year to do that, quite often you can include that notification in your consumer confidence report. There's 10 different elements that were required in a public notice: description of the violation, including the contaminants, when did it occur, what are the potential health effects to the public, is there subpopulations or populations that are specifically at risk for that contamination? Do they need to find other alternative water supplies, such as bottled water? What's the system need to do or doing to correct the problem? These are all required as part of the public notice, this information. What actions can consumers do to take to protect themselves? And when do we expect the problem to be resolved? And how can the customers contact you as the operator of the system to find more information? And then you always want to try and extend that to more people than the notice, because some people come out of town and work in the area. You want to make sure that everybody gets notified. So there's information on public notification rule. Once again, tier 1 notices as soon as possible, but no later than 24 hours of learning. You should also contact your regulatory agency, because they can assist and they need to know. Fecal coliform and E. coli violations fall into that. Nitrate or nitrate MCL violations. If you're adding chlorine dioxide and you exceed your maximum residual disinfection level, that violation is required a tier 1 notice. And then if you're a surface water treatment plant and you've exceeded your maximum allowable turbidity level, you would need to do one. If there's a confirmed water disease outbreak or emergency, you need to let to know about that. And any other violations that are identified by the primacy agency. We see there's a public notice rule, quick reference guide for that. And then what are we required to put into our consumer confidence report? So the consumer confidence reports are due out by July 1st. They cover the previous year. Well, we've got a column here for violations. So you need to note whether it was a violation, yes or no. What are the contaminants that we're testing for here in this first column? We need to organize them based off the type of contaminant. So whether it's inorganic or organic. Does the state have more stringent requirements? Because the state they have to maintain at least what EPA has, but they can be more strict. What are the MCLs? What are the MCL goals? A lot of the things, you have an MCL, but you want to keep, ideally, your goal is to be considerably less. What your results are. And then a key at the bottom that helps consumers or residents understand how to use the table. As I said, the distribution is required by July 1st of each year. If you got any questions, you should contact your primacy agency. And another thing to note is that you have to, after issuing the CCR, within 90 days or by October 1st, you need to notify your primacy agency. You have to certify that you issued and answer some questions in regard to that. So there's a quick reference guide for the consumer confidence report. And then we're on to our final poll. What would be wrong with collecting a coliform sample without having a dechlorinating agent in the sample bottle? A, the chlorine could damage the plastic bottle. B, nothing. Just write this on the chain of custody. C, the sample would not be representative. Or D, it would result in a false positive. All right, we've got 75% of the results are in. So we can see that the 78% of people put C, the sample would not be representative. And that is correct. So if we don't have any dechlorinating agent in the sample bottle, then there's always that possibility that there was a pathogen in there, but the chlorine continued to work on that and it killed that off before it got to the laboratory and was able to be tested. So it wouldn't really be representative of the quality of the drinking water. And so, all righty. So what have we covered today? Disinfection, dosages and feed rates, disinfection byproduct prevention, sanitary surveys, sampling and monitoring. What takeaways, what things do we want you to leave with? Water age management, and it can be dealt with in a multitude of different ways. It's important to make sure that we don't have issues. We can do it through proper tank turnover, through flushing, having the right size tanks and mains. Sampling and monitoring practices are important. We need to ensure that we've got proper disinfection, proper pressures out there, that we're doing our sampling correctly. And disinfection is important. If we look back to one of the first slides with the effects of, how we've had fewer infection rates since chlorine disinfection became popular. But we also need to make sure that we balance that with the formation of disinfection byproducts. So I want to take this opportunity to thank you all for participating. And as we said yesterday, if you get a chance and you want to share something that you enjoyed learning about today, please put that in the chat. And then I guess, we're here. I know we're right at the end, but we're here to answer questions. I believe Greg was going to jump back. So if you got any questions, please feel free to put those in the chat. Lori did put in the link to the Survey Monkey again and if you would fill that out within the next 24 hours to make sure that you can get your any continuing education credits that you might be looking for.
Great. Thank you, Daryl, for that very useful information and for offering the reminder as well about the SurveyMonkey link. We also appreciate your feedback on the webinar itself, which is also part of the SurveyMonkey evaluation and certification link. So we do have a couple questions. The first one was from Steve, and he asks, does anyone know of a current information source that would indicate where gas chlorine versus liquid chlorine would generally be more cost effective for a certain treatment plant size?
Well, my impression is that gas chlorine is from a purely a financial standpoint is typically it's better financially. However, there's all the regulations that go along with it and the potential to cause, serious, should you have a leak, to cause serious problems, not just at the facility, but it can get out into the public. I don't know, Greg, do you have any, of any studies that may indicate what's the best way?
I was kind of thinking the same thing as you, Daryl. The break point. I think there is a point between system size
There is.
where you get large enough where the additional safety cost and safety training becomes less of an impact to your budget. But for like a small system that's serving 1,000 people or something, the amount of cost savings, it would just be overwhelmed by the safety equipment and the hazards that you would have. So I concur. I took a peek at there is an institute, it's called the Chlorine Institute, and it's chlorineinstitute.org. I've looked at it before, and I'm not sure if they might have something on that, but it might be worth a look at that site.
Yeah, I think a lot of it comes down to, are you willing to take the risk? I think the costs for liquid or for gas chlorine are considerably less. And every one of them, there's no perfect answer. I mean, everything has its own issues. There's handling issues, between all three. They're handled different. Liquid dissipates, that 12.5% solution in a few months might be 10%. So there's a lot of factors to take into it.
Okay, thank you for that answer. And then I have a couple questions from Wendell. His first question, you might see there in the chat, is recent. If we are on tribal land, who would conduct a sanitary survey? So we'll go ahead and answer that one, and then I'll throw the second one out at
Okay.
you.
So it's my understanding that Indian Health Service conducts sanitary surveys based off my conversation with the gentleman who handles Michigan recently. He handles them. EPA, I think he does them on behalf of EPA because they are the regulatory agency typically for tribal lands. Greg, can you correct me if I'm wrong?
No, I think you're absolutely right. In Region 9, that's where I kind of
So you cut your teeth?
while I kind of accompanied some EPA people that came out. The EPA office there was in San Francisco, and some EPA people actually came out, and I was a technical assistance provider, and I came along with them, and EPA was there, but they hired an actual contractor that did all of Region 9. I'm not sure if that person is retired now. They must be now, but they did all of Region 9, which includes like the islands. There's like islands out where there's American territories, and they did all of the tribal
Yeah.
lands. So it varies, I guess.
Yeah.
Okay, thank you guys for that. The next part of his question was, how often should you flush out dead ends and what is recommended?
I think that if you were to start a program where you were flushing dead ends, you could you could keep an eye on, do some chlorine residual monitoring. I think that would be an indicator, if after a certain amount of time your residuals drop to a certain amount, that might tell you, now's the time to do it. I know they do have things such as automatic flushers, so you can have them set up so that they will just based off a certain amount of time, they'll automatically flush a certain amount of water, which saves, being able to have the staff time in order to go out there and actually do the flushing yourself. Greg?
Well, I was just thinking, the old school way of not letting your pipes freeze, you leave a faucet on. But maybe we could just do that. But I agree with everything you said. I'm just being facetious. But if if you had a problem and you did that once a month or something, I don't think that would be overkill. If in the summer months, and a dead end.
Well, and and the things that we have to consider here, are different than maybe Wendell has to, because we've got dry hydrants, and so you don't want to leave any water in them, and if if you leave them, if you're doing that in the winter, you're likely to have freezing. So we up here in the Upper Peninsula of Michigan, we'd probably operate a little different than Wendell may operate where he's at.
Okay, thank you. That was the last of the questions we had logged. So if anybody who's remaining in the session, if you have a question you'd like to pose to either Greg or to Daryl, please let us know. And I appreciate all the feedback that's coming in through the chat. Very kind words for you guys as our instructors.
Thank you.
Mm-hmm. So we'll keep the session open for a few more minutes and watch and see if anybody has any questions. We'll just sit tight for a little bit and we will let you know if we're going to close the session.